Welcome to our video lecture on topic 2.3, lipids. Our essential idea for today: lipids are a broad group of biomolecules that are largely nonpolar and therefore insoluble in water. Here's a lovely array of examples of lipids. Our objectives for today: we're going to outline lipid structure and function, distinguish among different types of fatty acids, which are one of the components of some of our lipids. We're going to outline the structure of triglycerides, define and calculate iodine number. We're going to describe hydrolysis of triglycerides. We're going to look at some of the energy content differences between lipids and carbohydrates and between lipids and proteins. We're going to describe structure and functions of phospholipids and wrap up with a little look at some steroids. When we're talking about lipids, we're referring to fats and oils. And the reason that they are nonpolar and therefore you're not soluble in water is because they've got these crazy long chunks of hydrocarbons. So remember from organic chemistry, each one of these little points is a carbon. It's got lots of hydrogens stuck to it because carbon has a valence of 4. It needs to make 4 bonds. Even though this fatty acid does definitely have this little bit of a polar end, the carboxyl group, which is what makes it a carboxylic acid and therefore a fatty acid, because that hydrocarbon chain is so big and so long, the overall molecule is quite nonpolar. We use our lipids for energy storage. These guys and carbohydrates are both used for energy storage, but lipids are better at longer term energy storage. It's easier for us to pack these lipids away and store them for a long time. We also have chemical messengers, hormones, that are lipids. A lot of them are steroidal hormones that are based on cholesterol molecules. We use them as insulators. Our animal friends that live at the poles definitely have a lot of lipid to insulate their bodies from the colder temperatures that are outside. And then, of course, our cell membranes are composed of phospholipids, and we'll look at those phospholipid bilayers of membranes a little bit later in this video. We're going to focus here a little bit more on those fatty acids. An example of lipids are fatty acids. All of them have that carboxyl group at the end, which makes them carboxylic acids. That crazy long hydrocarbon chain, again, makes them the fatty acids, makes them lipids. We can have some saturated fatty acids. Saturated means that they have no hydrogen deficiencies. They are as full of hydrogens as they possibly can be. Palmitic acid is an example of a saturated fatty acid. Each one of these carbons, because they're all single bonded to each other, all of our single bonded carbons, means that each one of those carbons has 2 hydrogens also bound to it. This is as many hydrogens as we can squeeze into this hydrocarbon chain. Our unsaturated fatty acids do have a little bit of hydrogen deficiency, and it is due to some double bonds between the carbons. Be careful, sometimes we're like, oh, there's a double bond between the carbon and the hydrogen. That is not even possible, my friends. So be careful, the double bond is not carbon hydrogen, it is carbon carbon. So we have a carbon carbon double bond in our fatty acid chain. We can have mono unsaturated fatty acids if there's only one double bond. We can have poly if there's more than one double bond. We can have some cis unsaturated fatty acids and some trans unsaturated fatty acids. So cis means same and trans means across. So when I form a double bond, sometimes I can keep the hydrogens on the same side, and that would be cis. We remove the hydrogens from the same side. There used to be hydrogens here, but now that we have this double bond, we have 0 hydrogens here. The hydrogens remain on the same side, and the hole that's created by the removal of those hydrogens is also on the same side. Then this whole molecule can kind of take over this chunk of empty space, and it will actually bend a little bit. So this kink in the fatty acid chain makes our cis unsaturated fatty acids a little bit healthier for us than are our trans unsaturated fatty acids. In the trans unsaturated fatty acids, we keep one hydrogen on one side of the double bond, we keep the other hydrogen on the other side, and so there's not really empty space on either side of the molecule, and so it stays a little bit more straight chain. That's not as healthy for us. We can talk about also some essential fatty acids. Essential fatty acids are those that we cannot make in our own bodies. We have to eat them. And 2 examples of essential fatty acids are linoleic acid and linolenic acid. So these two guys are essential fatty acids. You might be looking at these numbers here and wondering what they mean. So they're just kind of telling us how many carbons there are in the hydrocarbon chain. They're telling us how where those double bonds are in the chain. And sometimes when we buy vitamins, when we buy our omega-3, omega-6, omega-9 supplements, we're talking about where those double bonds are. So this guy is what we call omega-3 because that double bond is on carbon number 3, not from the carboxyl end, but from the other end. This guy, carbon 1, 2, 3, 4, 5, 6, this is going to be omega-6. And then this guy that I definitely scribbled all over up here is omega 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be an omega-9 fatty acid. Usually when we buy our supplements, there's in 3s and 6s and 9s. Notice that a lot of these, well, actually all of these numbers are even. In us animals, most of our fatty acids do have an even number of carbons. We can hydrogenate our unsaturated fatty acids. This is going to be a little bit of an organic chemistry review. Hydrogenation is an addition reaction. We're adding hydrogen to the molecule. So here I have my double bond. This is actually a cis unsaturated fatty acid because my hydrogens are on the same side. Cis is same. And then the whole that is created from the removal, that deficiency of hydrogens is over here, and that allows the molecule to bend. Again, this makes these fatty acids healthier for us because that bend prevents the fatty acids from packing together inside our blood vessels and causing strokes and heart attacks and whatnot. So cis is healthier for us. We can completely hydrogenate our fatty acids and add that hydrogen in where that double bond used to be. Now there's a single bond and I have hydrogens in those spots. So we've gone from unsaturated fatty acid to saturated fatty acid due to that hydrogenation. We can also sometimes have, as a side effect of this hydrogenation, we can have these trans unsaturated fatty acids pop up. Notice here that our hydrogens are on the opposite side of the carbon double bond, which means that this guy is going to have a little bit more of a straight structure, which allows it to pack inside our blood vessels a little bit more easily, which means that it's just not as healthy for us. We have in our data booklet, table 34, some examples of lipids, and there's also carbohydrates and nucleotides, but we're going to look just at the lipids for now. So we have examples of some lipids listed, and then we also have the structure of cholesterol shown to us. We'll talk about cholesterol a lot more at the end of this lecture. But I just want to take a quick minute to talk about how we can take this kind of structural formula and turn it into a picture of the molecule. So CH3, that's pretty easy to draw, CH3. CH2 looks like this. In this example of this molecule, there are now six of these CH2s in a line. So I have one already. I'm going to do 2, 3, 4, 5, 6. Good. So here are those 6 CH2s. At the very end of it, we've got our carboxyl group, so COOH. Then, of course, we would draw single bonds into all those pieces because that's the kind of bonding that we have. All of these guys are saturated fatty acids. They don't have any of those alkenyl groups. No double bonds in any of these guys. These last couple fatty acid chains definitely do have some double bonds, and we can see them here and here and here. So how I would draw this guy, I'm going to do CH3, and then we've got CH2, so CHH. I've got CH double C H CH2. And then I'm going to do that 3 times. So CH double CH CH2. We're going to do it again because I have to do it 3 full times. Here's number 1. Here's number 2. We've got C double C oh, I lost my H's and CH2. And then I'm going to do CH2 6 times until I get to my carboxyl group at the end. I've clearly run out of screen space. I'm going to stop there. But just be careful. Watch where those double bonds are. Make sure that you're checking for the numbers of repeats of each of those segments in the molecules. Good? Good. Triglycerides are formed from condensation reactions between a glycerol backbone. That's what we've got here is our glycerol backbone, and then 3 fatty acid chains, which is why they're called triglycerides. We've got glycerol and then 3 fatty acid chains. And those fatty acid chains can be all the same one. So notice that these 2 guys are exactly the same fatty acid chains. We could even have triglycerides that have all 3 of those residues. We call them fatty acid residues. This is residue 1 and residue 2 and residue 3. They could be all the same. They could be all different. We could have 2 of the same and 1 that is different. So lots of different varieties in the fatty acid chains in our triglycerides. We can see here's an interesting look at comparing how much saturated fat, monounsaturated and polyunsaturated, are in different kinds of lipids that we might buy at the grocery store. So butter has quite a bit of saturated, and then some monounsaturated. Coconut oil has so much saturated fat. Margarine looks like it's good for us because you're like, hey, there's only a little bit of saturated fat. And look at all of those unsaturated fats, except a lot of this is trans unsaturated, which is bad for us. So be careful with the margarine. Don't think that it's good for you. Good. Quick look at this guy, just a reminder about our unsaturated fatty acids. We can have cis and we can have trans, and this one, because the hydrogens are on the same side, because the whole left from the deficiency of the hydrogens is also on the same side. This is a cis unsaturated fatty acid, and it's mono because there's only 1 double bond. So let's go ahead and draw a triglyceride that is formed from glycerol. That's that glycerol backbone. Glycerol looks like this. We've got 3 carbons. They've got some hydrogens, and then we also have 1, 2, 3 hydroxyl groups on that glycerol molecule. Butanoic acid, this is the same thing as butyric acid. So in organic chemistry, I would call it butanoic. In biochemistry, sometimes we call it butyric instead. They are the same things. So butanoic acid, remember that our prefix for but is, but means 4. So I've got 1, 2, 3, 4 carbons, and then that hydroxyl group to make it oic acid, and then everything else is a hydrogen. I'm going to go ahead and draw it with my carboxyl group pointed toward that glycerol backbone so that I can actually form a triglyceride. So I'm going to draw again that carboxyl group next to the hydroxyl group on the glycerol. I've got my 4 carbons to make it butanoic acid. These are all oodles and oodles of hydrogens. Good. So in the formation of the triglyceride, this is a condensation reaction. Sometimes we can also call it dehydration synthesis. This is an example of anabolism because I'm taking smaller things and binding them together to make one bigger thing. I'm going to steal the hydroxyl group from the carboxylic acid. I'm going to steal a hydrogen off of the hydroxyl group of one of the glycerols. I'm going to steal a hydrogen off of one of the hydroxyls of the glycerol. This guy is going to be removed and it's going to form some water. So I've got 1, 2 H's and an O, H2O, that's water. This is why we call it condensation. But now, because that water has been removed, I'm definitely missing a bond. This carbon should have 4 bonds, and right now it only has 1, 2, 3. Oxygen should have 2 bonds, right now it only has 1. So the oxygen here and the carbon here are going to bind to each other, and this is going to create, my friends, what do we call carbon single oxygen, carbon double oxygen? This is an ester. So this group here, this organic group, is an ester. We formed some ester bonds in this condensation reaction. For the formation of the triglyceride, I'm actually going to do that not just here, but also here and here. I'm going to pause the video and draw it super quick and come back because you definitely don't want to watch me draw. It's going to take a hot minute. So here are the 3 ester bonds that we've just made. Ester number 1, ester number 2, ester number 3 on our 3 hydroxyl groups from that glycerol molecule, our 3 butanoic or butyric acid fatty acid chains. We now have a triglyceride. Good? Good. It's hard to know in a mixture of triglycerides exactly how many double bonds we have. So we can actually experimentally determine the average number, at least, of double bonds per unit of mass by reacting with iodine. Remember that iodine is diatomic, which is why it's I2. And when I have just plain old iodine, elemental iodine, it's kind of a brownish, purplish-brownish color. And I can add that iodine to my unsaturated fatty acids that have these double bonds, these alkenyl groups. An addition reaction will happen. The iodine will add itself to those double bonds, turn that double bond into a single bond, and then we'll have iodine added in where we used to have double bonds. When the iodine is here in the molecule, it becomes colorless. So we can basically carry out kind of like a titration investigation where we add a little bit of iodine. It goes from brown to colorless. We add some more. It goes from brown to colorless. But at some point, we've added enough iodine to completely add to all the double bonds. There aren't any double bonds left to for iodine to get added to. And so we can drip one more drip of iodine in and it'll stay brown. And at that point, we know that we have reacted with all the double bonds, and we can calculate with some amazing stoichiometry just how much iodine we had to add, and that can tell us how many double bonds there were in our triglycerides. And we call that the iodine number. So the iodine number, the number of grams of iodine that will react with 100 grams of a lipid sample. And again, this is this addition reaction where we can see the iodine going from brown to colorless as it adds itself to those double bonds, the unsaturated pieces of our fatty acids. So let's go ahead and practice a little bit of a calculation with iodine numbers. So let's say that our problem is that we want to figure out the volume of 1 molar, so we have 1 mole per cubic decimeter iodine solution, so iodine aqueous. And I want to find that volume in cubic centimeters. And I want to know what that volume is that would be required to exactly react with 1 gram of linoleic acid. Gives us the molar mass, which is kind of nice. I don't have to go and calculate it. So molar mass, 281 grams per mole. And this is my structural formula for linoleic acid. So what I'm going to do is start with that 1 gram, my 1 gram of linoleic acid. I'm just going to write LA because I definitely don't want to write that whole formula in my railroad tracks here as I do my stoichiometry. Step 1, always convert our grams to moles. So I'm going to turn our grams of linoleic acid into moles. There's 281 grams per 1 mole because there's the molar mass right there. Next up, I want to figure out how many moles of iodine are needed to react with this many moles of linoleic acid. Notice that I have 2 total double bonds. So I need 1 iodine here and 1 iodine here. I need 2 moles of iodine for every 1 mole of linoleic acid. 1 to go here and 1 to go here. Good. So now I can cancel out my grams. We can cancel out our moles of linoleic acid. And I have moles of, I shouldn't have canceled out moles here. We've got moles of iodine left. So when I do this math with my handy dandy calculator, 1 times 1 divided by 281 times 2 divided by 1, and we get 0.00711. 7 lots of digits, moles of iodine are required. But I want to find the volume of this solution of iodine. So if I have 0.007117 moles per cubic decimeter, I'm solving for those decimeters, and that's going to equal 1 mole per cubic decimeter. Multiply both sides by x. it's going to cancel out those DM3s. And so I now have 1 times x, which is the same thing as x, cubic decimeters instead of moles of my solution. So I need 0.00711. I'm going to make that a 2 for my sig figs. That 7 is going to turn that 1 into a 2. Cubic decimeters of solution, but of course this is in decimeters and my question asks for centimeters. So I'm going to multiply by 1,000. 1, 2, 3. 7.12 cubic centimeters of 1 mole per cubic decimeter iodine solution would be needed to react with all of that linoleic acid, turn all of those double bonds into single bonds. The last couple slides we're looking at how we can hydrogenate or carry out addition reactions with the alkenyl groups, the carbon-carbon double bonds in the fatty acid chains. But now we're going to look at a bigger picture and talk about how can we hydrolyze, break down whole big chunks of triglycerides. So how do we hydrolyze, break down our lipids? So catabolism of our triglycerides. A couple different ways that we can do it. We can add some lipase. Lipase is a protein enzyme that is produced by the pancreas, dumped into the small intestine. This is how we digest triglycerides in our biological systems. We take that triglyceride, we add some water because it is hydrolysis, right? We need to add some water. Notice that we have 3 water molecules. I need 1 for each of those ester bonds in the triglyceride. Lipase is a protein enzyme. Here's a picture of horse lipase. I know it's kind of random, but this picture was just so nice I couldn't resist. That lipase is going to break our triglyceride down into glycerol and those 3 separate free fatty acid residues. So residue 1, 2, 3 with our carboxyl groups back, residues 1, 2, 3 when they were still stuck in the ester bonds with the glycerol backbone. Since I have this very beautiful image of lipase here, I thought we would remind ourselves about some super cool protein structure pieces. Here showing us the C-terminal end of the amino acid chain that forms this lovely protein. So this is the carboxyl end, so I've got COO and an OH. Over here is my N-terminal, so we've got the amino group is sitting over here. We've got lots of amino acids in this primary sequence of this protein, this enzyme protein. And then notice some of the super cool secondary structure that we can see here. I've got this lovely curly Q. This, of course, is going to be alpha helix held together by hydrogen bonding between different amino acids due to those intermolecular forces between the carbonyl group of one residue and then the amino groups of another residue. Over here, notice these arrow, ribbon arrow things. This is showing us some beta-pleated sheet. So again, this is one way that we can hydrolyze our lipids. We can do it with lipase, this enzyme that is a protein produced by the pancreas, dumped into the small intestine. We can also hydrolyze lipids by using acid as a catalyst. So we can add a strong acid like hydrochloric acid or sulfuric acid, and it can act as a catalyst to hydrolyze our lipids. We, of course, are still going to need 3 water molecules in here. And we're once again going to break this bond. We're going to throw hydrogens back onto the hydroxyl groups that form that glycerol backbone. And then the carboxyl group, the double O, will get put back here as we add an OH again from water. So another way that we can hydrolyze our triglycerides is by using acid as a catalyst, and then we'll get our 3 fatty acid residues as free fatty acids, and our glycerol chain will be put back. One final look at hydrolysis of lipids. One other way that we can hydrolyze our lipids is with a strong base, and this one's a little bit different. So these 2 guys were acting as catalysts. They were not consumed in the reaction. They just helped water carry out that hydrolysis. It's a little bit different when we add strong bases because the base is actually consumed in the reaction. So the OH of the base is actually going to help to put back that hydroxyl group on the glycerol backbone. The metal that is in our base, that cation, is actually going to jump into the molecule also, and we're going to form what we call a fatty acid salt. So fatty acid salts are produced. So I don't just have fatty acid residue, I don't have that carboxyl group quite back here because I have this cation stuck in place of one of the hydrogens that we would have gotten if we had catalyzed our hydrolysis with lipase or an acid. We still get glycerol. Glycerol looks the same, but instead of having free fatty acids with carboxyl groups, we now have salts that have that cation, that metal cation, and then the rest of the fatty acid chain. What's super cool about these fatty acid salts is that this is what makes up soap. So this reaction is known as saponification. This is saponification. We can combine triglycerides, fats, and oils with some kind of strong base, so sodium hydroxide or potassium hydroxide. Sometimes we call this lye. Historically, that's what we used to make our soaps. And we get these super cool salts that we can use to wash things. How even do these soap molecules work? Let me tell you. So we've got that sodium group here. Sodium is a cation. It has a charge, and so this little piece is hydrophilic. It will dissolve in water. It's attracted to water, can form some dipole moments with water. The other chunk, the fatty acid hydrocarbon tail, is definitely hydrophobic, is going to be repelled by water. So if you have grease, oil, some other chunky hydrophobic thing stuck to your hand or your clothing, what happens is the formation of a micelle. So a micelle is going to have the fatty acid hydrophobic, the hydrophobic part of the molecules will be pointed toward the oil, the grease, the dirt, whatever it is that needs to get off our clothes, off of our hands. The hydrophilic head, where that sodium cation is going to point out toward the water. And the positive charge here and then the negative polarity, that partial negative charge on the oxygen of the water molecules, are attracted to each other, and so they can form these dipole intermolecular forces. And so the whole thing will happily dissolve in the water, whereas the oil by itself would not. It was repelled from the water. So this micelle, this little bubble of soap molecules, where we have the hydrophilic parts pointed out toward the water environment, the hydrophobic tails pointed in toward the dirt, the grease, the oil. It's how soap works, and it's so cool. And be careful, my friends, because sometimes super fancy, expensive soaps are like, ooh, we have micellar action. Dude, that just means it's soap. So don't spend crazy numbers of dollars on micellar action, because it's literally just soap. That's all it is. All right, so hydrolysis of lipids is also how fats can spoil. And sometimes we call it rancidity. When fats go bad, when they spoil, they are rancid. We can definitely accelerate this spoilage, this hydrolysis of our lipids using enzymes or acids as those catalysts. What's kind of interesting is that some of our fatty acids can actually become autocatalytic. So as one thing starts to break down, it stimulates the breakdown, the rancidity of more of the triglycerides. Some of our fats and oils can go bad because bacteria gets into them, and the bacterial enzymes will actually increase the rate of the hydrolysis of those triglycerides. It is often oxidative rancidity, where oxygen is jumping in there and breaking down those double bonds here, or breaking down the esters a little bit. Interestingly, this is often accelerated by sunlight. So if we package our fats, especially the polyunsaturated fats, in something that prevents light from getting to our our foods, then we can protect those double bonds and prevent them from going bad too quickly. We can also add antioxidant preservatives, which will be oxidized first before our fatty acids are oxidized. This guy is a super cool preservative, antioxidant preservative. This hydrogen will pop off and this molecule will be oxidized more easily than the fatty acid chain will be oxidized, which is how it prevents the fatty acid chain from being oxidized. It itself gets oxidized more easily. Energy content. So this is a quick, easy idea. So fats have super huge amounts of energy per unit of mass. So 37 kilojoules on average per gram of fat. Oodles and oodles of energy stored in the fat because it's just not as oxidized as these other pieces. So carbs and proteins, kind of similar. Alcohol, interestingly, has quite a bit of energy still stored in it, which is why these guys are kind of good as biofuels. But when you're 21, be careful, don't overdose on the alcohol. First, because it's not healthy, but also because there's a lot of what we call empty calories, lots of energy without a lot of nutrition. So be careful. Be careful, moderation, but only once you're 21. Good. How do we know the content of energy in these different biopolymers? We use these super cool things called calorimeters. Our calorimeters, we can burn the food in here. We have the electrodes, these ignition wires that will spark and then burn the food in this little reaction vessel. There's water surrounding the reaction vessel. All the heat that is produced as the food combusts is released to the water, and then we can measure the temperature change of the water, and then we can do some super cool thermodynamics, energetics, Q equals mc delta T, to determine how many kilojoules per gram we have stored in our foods. Just a couple more ideas, my friends. I promise we are almost done here. So phospholipids are super cool. They're kind of like triglycerides, except instead of having 1, 2, 3 fatty acid chains, that third fatty acid chain is actually a phosphate group instead. So we have 2 ester bonds, so we still have those 1, 2 ester bonds that we are used to seeing in our triglycerides, but that third bond, instead of just being a plain old ester bond, is a phosphate ester bond. So we throw this phosphate group in here. What's super cool about these guys, kind of like our soap molecules, those fatty acid salts, they're going to have a polar piece. So this one is quite hydrophilic, the polar group where the phosphate group is, and then we have our hydrophobic fatty acid tails. And so when we are building our amazing cell membranes, we're going to put the hydrophilic heads, where the phosphate groups are, out toward the environment that has lots of water in it. We'll also put those phosphate heads that are hydrophilic in toward the inside of the cell, which also has lots of water in it. The tails will actually sort themselves near each other in the middle of that bilayer because I have phospholipid here and here. So all of this region is hydrophobic, no water. Out here, the hydrophilic heads, the phosphate heads, are super happy to be around the water environment that's outside the cell and inside the cell. What's interesting about our cell membranes, these phospholipids, and really all of our lipids, they don't form polymers the way that our proteins, that our carbohydrates do. When we talk about proteins, we talked about those amino acids that bond together with actual chemical bonds, these covalent bonds between amino acids, those amide linkages that are covalent bonds, peptide bonds. In our lipids, what happens is lots of really strong London dispersion forces. So we have weak hydrophobic interactions between each of these fatty acid chains. So they are attracted to each other because they're repelled by the water. But when we put so many of them together, the sum of all of those weak London dispersion forces becomes a stronger sum of van der Waals forces. And this is what holds most of our lipid clumps together. Steroids. Steroids are another super cool kind of lipid. Steroids are going to be composed of 3 6-carbon rings, 1, 2, 3, and then 1 5-carbon ring. There's that guy. And this is considered the steroidal backbone of all of our steroid molecules. This is an example kind of showing all of those carbons, so carbon number 1, 2, 3, 4, all the way around in these rings, and then also out on those chains. So many carbons and hydrogens makes this quite hydrophobic nonpolar. So these steroids, cholesterol, don't dissolve in our blood very well because our blood is mostly water and these steroids are quite nonpolar. So how we can transport cholesterol and then also triglycerides through the bloodstream is in these super cool things called lipoprotein complexes or lipoproteins. So we've got a little chunk of protein in this bubble similar to the micelles that we were looking at when we talked about soap. We've got our hydrophilic heads of the phospholipids, so the phosphates are pointing out toward the blood plasma where we have lots and lots of water, so the hydrophilic phosphate heads out here, and then the tails will point in. But we do not have a bilayer like we do in our cell membranes. Instead, we just have a monolayer, which means that the inside of this bubble, kind of like the micelles that we were looking at in our soap, the inside is all quite non-polar, hydrophobic. And we can bundle up our triglycerides, we can put some cholesterol here inside the bubble of phosphate, phospholipids, so that the whole thing can be transported around the bloodstream as a bubble. What's kind of interesting is that we have some of these guys, some of these lipoproteins are quite good for us. These high density lipoproteins is considered our good cholesterol. The more of this we have, generally the healthier we are, the lower our blood pressure, the lower our risk of heart attack. As we have low density lipoproteins or very low or giant crazy sauce heart blocking lipoproteins, these guys are bad. So the bigger they are, the more likely they are to stick in the stick to the insides of our blood vessels, build up. So atherosclerosis, which can lead to narrowing of the blood vessels, which leads to high blood pressure. Sometimes chunks of this can pop off and then they get stuck further down the blood vessel, and that can lead to heart attacks and strokes. So bad. Watch your blood cholesterol levels. Stay healthy. And our last little piece for today, steroidal hormones. We do have lots of hormones that are based on cholesterol. Notice these guys look a lot like cholesterol. So we've got corticosteroids, which are going to regulate metabolism and immunity. So cortisone, cortisol. Sometimes we call these our stress-related hormones because we do tend to change the amount of cortisol, especially that we make when we are feeling stressed out. We've got some sex hormones, so estrogen, progesterone, testosterone. These guys are all reproductively active hormones. And then we have some anabolic hormones. Our growth hormones are involved in the synthesis of muscle and bone. And all of them are based on those steroid molecules. They look a lot like cholesterol, right? Good. We did it. Objectives accomplished. We talked about lipid structure and function. We talked about those different kinds of fatty acids. We have saturated, we have unsaturated, we have polyunsaturated, we have trans unsaturated and cis unsaturated. We talked about triglycerides, which is that glycerol backbone. And then we have those ester bonds where they're attached to our, I am not drawing this very well at all, where we are attached to those 3 fatty acid residues. We talked about that iodine number, how we can figure out how many double bonds we have in our lipids by looking at how much iodine they can react with. We talked about how we can hydrolyze our triglycerides. We can use enzymes. We can catalyze with acids, or we can react with our strong bases and make soap, which is super cool. Our lipids have way more energy per gram than do carbohydrates or proteins. We talked about phospholipids. They're pretty cool, kind of like our triglycerides, but instead of having 1, 2, 3 fatty acid chains, they only have 2 fatty acid chains and then 1 phosphate group instead. We looked at those steroids, cholesterol, estrogen, progesterone, cortisol. We did it. Good work.